Okay. Um, Hello, everyone, and welcome to this Introduction to Arkouda demo. We're going to be talking about some very basic operations, some background, and how you can use Arkouda in place of pandas or NumPy to do exploratory data analysis. So let's start with what Arkouda is. Arkouda is an application that's meant to bridge data scientists and high-performance computing systems. So Arkouda is a simple app that works on a client-server model that provides you, the data scientist, with a Python interface that you can be running on your laptop or on your personal computer. Um, and the operations in Arkouda happen on a large scale. That can happen on the server that can run anywhere from, again, your laptop to a supercomputer to the cloud, a VM, a cluster, anything. The idea is for this tutorial to help you understand the basics of Arkouda, the core features, and to learn how to leverage it for scalable data analytics. So why do we want to use Arkouda over Pandas or NumPy? Most of the time, when you're working with large quantities of data, all of that data is usually too big for your laptop or computer's memory or even storage sometimes. And that makes it really hard for data scientists to do meaningful computations with their data without having to downsample something, which sometimes misses the things that you might be looking for in your data. So unlike pandas or NumPy, which operate on a single node, Arkouda leverages the ability of being distributed or being running on an HPC system to perform its computations in parallel, making it ideal for large-scale data analytics tasks and distributing all the data that you have across multiple nodes. So as I mentioned earlier, Arkouda operates on a client-server model. The client is a Python script or a Jupyter notebook that you interact with, and the server is written in a language called Chapel. Chapel is a programming language designed for productive parallel programming, um, which enables the distributed nature of Arkouda. So all the computation that happens on the server is powered by Chapel. The client itself has a handle to the data that's living on the server, and that's distributed across the server, but the client itself does not store any data. This is the basic idea of enabling large-scale data analytics using this client-server model. Right. What if you don't have an HPC system to distribute your data? You can still run Arkouda. The server doesn't have to run on a different machine than what you're operating on. It can run on your laptop just fine. Just that you will be limited by your laptop's memory. You can run it on cluster, cloud, whatever you'd like. Arkouda also has this concept of modules. So Arkouda is modular. So therefore, you can just pick and choose which modules you want to include in a server. For example, if you want to make a customized lightweight setup tailored to your use case, or it also enables you to add more features to Arkouda using rapid prototyping and productive programming using Chapel without a lot of overhead. If you want to learn more about Arkouda, you can go to the website linked here and the installation docs, and we will be sharing this notebook publicly. All right, so some of the things that we'll be covering today is how to launch and connect to an Arkouda server, some basic array creations and manipulation, working with data frames, basic EDA operations like groupbys, plotting things by transferring data back to the client, file I/O, and a sample EDA workflow that uses squirrel data, which is going to be fun. All right, so first things first, how do you launch and connect to an Arkouda server? So after you install and build a server, you have to launch it in a separate process on the machine that you want the server to be on. So this is going to be your big machine if you have like a supercomputer or a cluster, not your laptop. So you can open a terminal like this, and you simply type Arkouda server. Oh, wrong cell. You simply type Arkouda server and then a number of locales that's appropriate for your system. In this case, I'll just say 2 locales because I want to run it on 2. And once you execute that, oh, misspelled server. Once you execute that, it's going to launch it up and it's going to inform you which node the server is running on. So this is the node, this is the port. We will need this info in order to connect to our server. So we put this node and port info in here. And once we hit that, we're going to be able to import Arkouda and connect to the Arkouda server as such. Going over some other basics of arrays, Arkouda uses PD arrays. These are very similar to NumPy's ND arrays. PD here stands for parallel and distributed. This is a reference to how the data lives on the server and is distributed across all the nodes of the server, in this case, 2 nodes. You can have multidimensional PD arrays in Arkouda too, but the server must be built to support multidimensional arrays. We also have support for other types of arrays like sparse matrices using the SP array class, but those are prototypical, and we won't touch on them in this tutorial. So some of the simple operations that work that should look really familiar if you're coming from a NumPy world. You can create arrays, ranges from 0 to 1,000, linearly spaced elements between a given bounds, random arrays of a certain value. One of the things to note here is that all of this data, all of the arrays that we're creating, is not living on my laptop. It's on the server that I just launched this process on. Launch, in the terminal. So when the array is small, you get to see all of the elements. But if the array is really huge, like 1,000 elements or such, Arkouda won't transfer all of the elements back. This is just save space because we don't know that if the whole array is even going to fit on your laptop. In this case, 1,000 elements array will easily fit, but the array could have trillions of elements. So it only shows a select few, the first 3 and the last 3 in this case. Other things like element-wise arithmetic operations work exactly the same as they do in NumPy or simple Python. There's nothing special in terms of what you write, but in the background, everything, addition, multiplication between 2 arrays, assigning square roots, element-wise operations like absolute or summary operations or scan operations like the cumulative sum, they're all happening on the server. So they're happening lightning fast or powered by Chapel, and they're happening on the server. You don't have to fit these things on your client. One important thing to note here is that since everything lives on the server, iteration over a PD array in the style of 4x in array is an anti-pattern. It's not supported in Arkouda. This is because if you iterate over an array element-wise like this, you're going to be transferring these elements from the server to your client. And usually that's not what you would like to do. You want to express the computation that you want to do in a more array-based approach. However, in some cases, if you really want to transfer the data from the server to the client, for example, if you want to plot it or use some other Python library with it, you can use the toNDArray function, and that'll convert the the Arkouda PD array into a NumPy ND array. Any questions so far? I don't think I can see hands, so if you have a question, please just interrupt me. Okay, next up is sorting. So Arkouda is one of the most powerful and performant sorting routines, and it can scale up to thousands of nodes, sorting terabytes of data per second. This is a sample run that we'd done on an HP Cray EX machine that scaled up to more than 8,000 nodes, sorting close to 9 terabytes of data per second using Arkouda's argsort. So there's a couple of different routines. There's more than this. ak.sort just sorts an array as is. And argsort, you might be familiar, returns the permutation of indices which sort the array. So if you have this case, if you have like a random array A, and you calculate the permutation of the indices that will sort the array using argsort as such, this is going to tell you that, hey, the smallest value in this array lives at index 3, which is right here. The second smallest lives at index 8, which is the same value technically, but it still lives there. The third smallest lives at index 1, and so on. And if you apply that permutation to the array like this, you get what's a sorted array. All right, that's pretty simple. Data frames. So now we're transitioning into the pandas world from the NumPy world. So Arkouda has a data frame class, which is very similar to pandas data frames. You can create Arkouda data frames through pandas data frames or through Python dictionaries. And you can perform all the operations that you'd expect to be able to perform on a data frame, like merging, groupbys, and even converting between pandas and Arkouda's data frame types. All right, so say you have a few arrays like this, you have an alien ID, you have a bunch of different species, you have the corresponding tentacles that the species has, and you have the snacks that the species likes, and the mood. You can create a data frame in Arkouda calling the ak.dataframe call, and you pass it a dictionary of the keys and the array values, And when we print out the data frame, this data frame lives on the server. Similar to how we don't print all of the information all the time. When we're printing out arrays, we don't print out all the information all the time when we're printing out data frames. Sometimes if we have too many rows, it's going to skip some of the middle rows. If we have too many columns, we're going to skip some of the middle columns in printing out because we don't want to transfer too much data. Things like selecting a single column, indexing into a data frame, selecting certain elements out of the data frame, all work exactly the same as they do in pandas. There's nothing special. You can also convert between Arkouda's and pandas data frames, as I mentioned. For arrays, there's a toIndy array method. For data frames, there's toPandas, which will convert the Arkouda data frame to pandas, and it will transfer all the information in there to the client. So you need to be mindful of, all the data transfers from the server to the client. And again, this is the same data frame, but we called toPandas on it, and now it lives on the client instead of on the server. You can also change a pandas data frame into an Arkouda data frame. So right over here, I created a pandas data frame using pd.dataframe. And then if I pass that pandas data frame into ak.dataframe, it's going to give me an Arkouda data frame that has the same data. It's going to send all that data to the server. We can also merge two data frames calling the merge functions. And this is the same as a SQL style join, a left join, or a pandas merge. They're all the same. So in this example here, we created two data frames above. Both of them have the species column, which is common between the two. So we can merge those two data frames on the species column. So if we do that, we're going to get this merge data frame. All right, so merging data frames works the same way. We can see that the two data frames that we had above, one which talked about the species and their homeworlds and the average number of calories that they have in their average snack and such, merged with the information about the species ID, the tentacle count, and their mood, and the snacks themselves that they like. And we see that everything's been merged on this species over here. We can use groupbys in Arkouda. So just like you can do groupbys in pandas, you can do groupbys in Arkouda. And you can perform aggregations like count, mean, sum, min, max, whatever you can dream of. GroupBys in Arkouda are powered by Arkouda's ArcSort, which is highly performant, and by extension, GroupBys in Arkouda is also really performant. And GroupBys are usually the bread and butter of most data science operations. So Arkouda is really good at that. So you can ask simple questions like, hey, group by their homeworlds and see what's the average tentacle count for each of these different homeworlds. So you get that. Or you can ask something different like, hey, what's the average snack calorie intake by mood? Like, how many calories did they intake? This doesn't make sense for this data set, but it might for some other data set. Or we can ask more specific questions like, hey, how many tentacles per calorie do these different creatures have? And we can see that we added an extra column to our data frame over here that says tentacles per calorie. And this all happened in parallel on the server where we divided one of the columns by a different column. All right, plotting. So you can use any of the Python libraries that you like to plot the data that you have in your Jupyter Notebook. But before you do that, since the plotting libraries only work with data that's on the same machine as the Jupyter Notebook is, we need to transfer the data from the server to the client. This is one of the cases where a data transfer is needed. So for example, here we're trying to plot the tentacles per calorie, but we want to make sure that the tentacles per calorie is greater than 0. So we take those columns out of the data frame, we filter those, and this toIndy array call over here, these two calls, is what's doing the transfer from the server to the client. And you can plot this using matplotlib, and you get this nice little information of the nautilins being the highest tentacles per calorie count. All right. Any questions about the different operations that I've showed so far? Okay, cool.
No question, but very cute examples.
Thank you. Now we're going to dive into an even more fun little demo, and this is using the Squirrel Census data, which is a census that happened in Central Park, NYC, where people self-reported seeing squirrels and what they were doing. So if you see a squirrel in Central Park, you fill out the survey, and it tracks the data. It has over 3,000 squirrel sightings. and things like their color, what they're doing, what sounds they're making, if they're interacting with humans, running away from them, things like that. And we're going to try to do some EDA on this data set. So what we'll discover, we're going to read the file that has the data, and we're going to look at what the data set looks like. We're going to try to classify squirrels by their fur color, by their activities, by their friendliness, and looking for some really specific kinds of squirrels too, and then do some more graphing and plotting. All right, so how do we do file IO in Arkouda? That's pandas, my bad. To read a file in Arkouda today, we can use a couple of different file formats. So we can have Parquet, HTF5, and CSV. Usually, when possible, we want to use Parquet and HTF5 over CSV because the performance with these formats are much, much better. And when writing files out to disk, Arkouda writes out one file per locale that your server is running on. So if your server is running on 16 locales, 16 files will be written because the data itself is distributed across these different locales. So each file will own have one corresponding locale to it, and it'll be suffixed by the locale name. We're adding more formats like ZAR and etcdf in the future. So reading Parquet files is really simple. You have the data path, and then you call read Parquet on it, and it's going to read it into a dictionary. You pass a dictionary to aka.dataframe, and you get the data frame. So reading this really quick, we can get some characteristics about the different columns that this has. The shape, we have over 3,000 rows and 31 different columns. And as I mentioned earlier, Arkouda doesn't always print all the rows in the columns, so you can see that we skipped over some of the rows in the middle here because we don't want to print too many. And the same thing with columns too, because there's 31 columns is too many for Arkouda to reasonably transfer from the server to the client just for printing purposes, so we skip over some of the data. So this is just to give you a snapshot of what the data looks like. So we can cover things like X and Y are the coordinates for where the squirrel was found within Central Park. The unique squirrel ID is to track the same sightings with multiple squirrel. Hectare is like a grid of Central Park with like north to south being the letters and east to west being the numbers. Shift is AM or PM when the squirrel was sighted. Dates when squirrel was sighted. The age being adult or juvenile, things like that. The sounds that the squirrel was making, the cucks, quads, and moans are the different sounds that the squirrel makes. Tail flags and tail twitches are different behavioral cues for the squirrel. And these three columns are if the squirrel was seen approaching humans, seen indifferent to humans, or seen running from humans. And any notes about other interactions, which are mostly empty because people don't fill out all survey boxes usually. All right. So a very basic group by, like we saw earlier, is to group the data frame by the primary for color and count some token column just to make sure we don't get all the columns in the output. We run that really fast group by. We see that all 5 out of 6 squirrels are gray, and some are cinnamon, followed by black being the least common. And then 55 of the rows, we didn't actually have any primary for color selected. Excuse me. We can do more complicated group bys, like activities by the time of day. If they were running, eating, chasing, or climbing, or foraging in AM versus PM times, and group them by fur color too. So we convert these Boolean columns to integers to make sure Arkouda's group by does not remove them. We want to count them, and that's the current limitation. And then we choose the activity columns, which are these 5 different activities that squirrels can be doing in the survey. And then we group by the shift and primary fur color and sum up the activity columns. And this is the same syntax that you'll find in pandas. There's very little difference between pandas and Arkouda in this case. And you get this nice little data frame, which groups the shift by AM versus PM, what the gray squirrels were doing, what the black squirrels were doing, and what the cinnamon squirrels were seen doing. We can ask different questions, which involve slightly more complicated math and assigning points to their friendliness. So if you see a squirrel approaching humans, we give it +2 points. If it's indifferent to humans, it's +1 point. But if it's running away from humans, -2 points for that. You create an extra column in the data frame called friendliness score. That's based on some product of the other columns that are already in there. And you group by the unique squirrel ID and friendliness. Sorry, you sort them, and you print out the top 5 most friendly squirrels. So these are the the friendliest squirrels, they all seem to have a friendliness score of 3. All right. Another thing that Arkouda is really good at are things are questions that are really, really specific. So example, I'm looking for gray squirrels that were making quaz sounds, and they were either eating or climbing and twitching their tail at the same time. So a specific question, not super complicated, but these queries can be as complicated or as convolved or as simple as you'd like. So we do this operation on the data frame that we have to find these quirky little squirrels. And we see that out of the 3,000 squirrels that we have, there are only 3 which satisfy these requirements, that they're gray, they're making the quaz sound, they're eating or climbing and twitching their tail at the same time. And all these things have certain meanings. All right, so let's plot some of the information that we've got here. So this is the same group by about the fur color counts that we can convert to pandas, as we saw earlier. We retain the index to make sure that the axes of the graph get the information about the names of the colors that we have. And here's a simple fur color distribution that's more graphic. This is the same computation again. We're just using matplotlib to plot these things in order to make better, glean better information, make better inferences from the data. Things like this, squirrel time of day activities. So looks like squirrels are more active during PM. Why could this be? Or does it really explain why we see more activities by time of day? Does this necessarily mean that squirrels are more active during the evening? There could be another explanation that a data scientist might argue for, is that when do people go to the park? It's during the evenings. And this is a survey based on people seeing squirrels. So maybe there's just more, findings, more entries during the PM shift, and that's why we see more activity, squirrel activity during the PM shift. And we might want to ask, hey, what's the relative number of AM versus PM entries that we have in our 3,000 rows, and things like that. We can also do histogramming in Arkouda using the histogram method to bin our data into different into bins, and then send that back to the client for plotting. So ak.histogram here, we're binning the friendliness score into 10 different bins, and then we're sending those bins and the histograms to the server to plot using matplotlib. And we get a case that most squirrels here are pretty indifferent to humans. They have a score of 0, 1. The second runner up here are squirrels that don't like humans, score of -2, and a very select few actually really like humans with a score higher than 1. Another interesting that we could potentially graph on the map is that for the 3 squirrels that we saw earlier, who were our quirky squirrels that were doing the things that we wanted them to do, where it was like, hey, are they eating or climbing, twitching their tail at the same time, and a couple more things I can't quite remember. Oh, they were gray and they were making the quaz sound, right? Maybe we want to ask, where do these squirrels live? And this is a very specific problem, right? Like, we want to find a very niche kind of squirrel here. And we can send that data, drop the NA values, send that to pandas, and then plot it using matplotlib. And we get a very interesting graph here. Out of those 3 squirrels, 2 of them are living on the opposite corner of the park. One's at the bottom left here, and one's on the top right here. And the third one is still close to the top corner. This very interesting observation. A data scientist might be able to glean some very good insights from them, like, why are these squirrels over here? The data set described the tail twitching, meaning in squirrel body language, to express curiosity. So perhaps the city itself is what's making the squirrel curious, because within the park it's sort of a natural habitat, but outside it's New York City. It's busy buses and buildings and whatnot. So maybe they're twitching their tails because of that. Or maybe that's where the trees are, because one of the filters that we had was climbing. So maybe that's where the trees are. That's where you'll feasibly see the squirrel climbing and other things like that. So this is all to help the data scientists make some good info, gain some good insight from the data that they have that may be massive, and they want to filter it down, but without having to downsample anything. All right, and that's actually the end of the demo that we have prepared. one small thing that we can add is once you're done with your EDA operations, it's usually good practice to shut the server down. So if you run that, it's going to shut down the server and disconnect you as well. If you don't want to shut down the server, say, for example, if other people are using it too, you can just disconnect from the server for your process. Alrighty. Any other questions? Cool. Thank you for joining.